We will study the reactions of carboxylic acids and their derivatives in Chapter 22. Most importantly, we will focus on nucleophilic acyl substitution reactions. If you recall from Chapter 20, type 2 carbonyl compounds were introduced, and they were the carboxylic acid derivatives. They were especially different because they have a leaving group, that's Z, and it has a pair of electrons, at least one pair of electrons. Now, Z can be a chlorine atom, it could be an NH2, it's like an amine, OCH3, OH, and OCOR group. So for example, if we have Cl, this would be called an acid chloride. And if you have the OCH3, that would be called an ester, so on and so forth. Of course, it's an OR group, so it could be also an ethyl group attached here. That would be considered also an ester. So this is an ester. So let's talk about type 2 carbonyl compounds and their reactions. We saw again in Chapter 20 that when we used powerful nucleophiles, organolithium reagents, the Grignard reagents, hydride reagents, and sodium alkanides, we saw that the reaction was irreversible, meaning if we reacted the carboxylic acid derivative with CH3, let's say MgBr, let's say we have the acid chloride, we saw that the reaction went all the way, and I'm going to draw a last arrow here at the end, to making the alcohol. So if you recall, this is from Chapter 20. In between, the ketone was formed, but we said because we have a powerful nucleophile, the reaction kept going. So again, this is only a review. And then, of course, at the end, it was protonated, the carbonyl oxygen. So this reaction is irreversible, irreversible. You cannot go back to the carboxylic acid derivative, in this case, the acid chloride. Now, of course, in the last chapter, in Chapter 21, we explored reacting aldehydes and ketones with weaker nucleophiles, and we said those reactions were reversible. Now, we will apply concepts from Chapter 20 and Chapter 21 to acyl substitution reactions. But there is a very, very important piece of information here. And that is this statement right here. The acyl substitution product will depend not only on the reactivity of the type 2 carbonyl, but also on the leaving group ability of Z. So Z right here, Z is going to govern whether the reaction is going to take place or not, especially when you use weaker nucleophiles. So again, we're using weaker nucleophiles, water, alcohols, primary, secondary amines, cyanide ion, etc. So, or there are more, of course. So that's the highlight of this chapter. So let's begin. We're going to look at the mechanism and reactivity in acyl substitution reactions. So if we have this reaction right here where we have Z as the leaving group and we have a nucleophile, as you would have predicted, the mechanism is going to go this way. So the nucleophile attacks and you add the nucleophile. Notice how we have equilibrium because this is a reversible reaction. You also now have what? The tetrahedral intermediate. And what happens here is that there are electrons, lone pairs on the oxygen, carbonyl oxygen. Now what's going to happen is that they're going to come down and kick Z out. So now Z is kicked out. And now you have the nucleophile as a substituent that's added now, replace Z, and then of course you have Z minus. So what do you have now? What you have is you have acyl substitution. This whole process is called the acyl substitution. Because once again, this group is called an acyl group. So there was a replacement at the acyl group. Now, an important point to mention here is that the identity of Z is going to determine how the reaction will proceed, whether the reaction will take place or not. This is very, very important. So Z is the portion that will help you determine whether reaction is going to take place or not. So let's take a look down here. So the rate of the reaction depends on two factors: the stability of the carbonyl carbon derivative. So what are you starting with? If you're starting with an acid chloride versus a carboxylic acid or a carboxylate, and then of course the leaving group ability of Z minus. So if you recall, when it comes to the stability, we explored this in chapter 20. This was in chapter 20. We had inductive and resonance effects. All we need to remember is that on the bottom right here, this is the most stable, which means the least reactive. And at the top here, with the acid chloride, we have the least stable, most reactive. And again, we talked about resonance and inductive effect. They are going against each other. So if you recall, this had the best resonance. And this had the best inductive effect. Or at least the inductive overwhelmingly works here. And again, that led to the most important consequences, which are these. This is what you need to know. So now let's talk about the leaving group ability. The best leaving groups are weak bases. They're stable bases. The weaker the base, the better the leaving group. Weak bases are stable bases. And the reason why they're weak is because they do not want a proton. That's why they're called weak. Strong bases, on the other hand, want a proton. So that's why they are not as stable. So remind yourself of that from Organic 1. So let's look at the pKa's of the following carboxylic acid derivatives and compare their leaving group abilities. So let's talk about the pKa. The pKa of a acid chloride is -7. The pKa of the anhydride is around 5. Carboxylic acid is around 15. The ester is also around 15. And the amide is around 35. So this is, let me circle what I'm talking about. This is the pKa of the conjugate acid. So for Cl, the conjugate acid would be HCl. And the pKa of HCl is -7. It's extremely acidic, extremely acidic. Also, this is the pKa of the anhydride portion, the OCOR, the OH, the OR, and the NH2. So that means that as you go this way, you have an increasing base strength, but the opposite way means you have an increasing leaving group ability. So when HCl dissociates into Cl minus and H plus, Cl minus is a much more stable base. That's why it's down here. So this is the weakest base versus if you had an NH3 and it dissociates, let's say this way, NH2 and H plus, this would make it, this is a minus, strong base, and this is a weak base. So that's what we're trying to explain here. The best leaving group is Cl. The worst leaving group is NH2. So that's what you need to remember.